Oh, thanks, Jessica. So you are all on tape. It is my pleasure to introduce Aakanksha Naik from the Language Technologies Institute at Carnegie Mellon University. Aakanksha has done a lot of great work on studying these long tail phenomena in language. Also done a lot of great work in clinical NLP, clinical event extraction, so on. And of course, this summer, she was also here working with Tom, Hope, Sergi, and myself on kind of augmenting clinical predictions using literature retrieval. So I think we're all very excited to hear your talk, and I'll let you take it away.
Thank you so much for the introduction, Lucy. And hi, everyone. I'm super excited to be here and to be presenting our recent work on adaptation for long tail domains through the lens of a case study in clinical information extraction. So I'd like to jump into this talk by first explaining what I mean when I say long tail domains and motivating why this is an important problem for us to look at. So this is a quote from the Penn Treebank paper. A lot of you might have already seen this. And the Penn Treebank paper was arguably one of the first works that kind of pushed this paradigm of constructing benchmarks and using those as ways to evaluate and develop models in natural language processing. And their main principle was this thought that you can make significant progress in text understanding if you investigate phenomena that occur most frequently and most centrally in naturally occurring unconstrained free text corpora. And this was a worthy goal, and this ensured that the benchmark datasets that were constructed and followed the Penn Treebank paper all provided a common evaluation platform for models to be calibrated against and to be evaluated on. And since the Penn Treebank paper, there have been tons and tons of new data sets created, a lot of recent large-scale ones, such as SNLI, multi-NLI squad, and benchmarks have become a huge driving force in natural language processing today. I think a lot of us here are aware of the Hugging Face datasets library, which also recently won the Best Demo award at EMNLP 2021. And this indicates how important benchmarks have become as a resource for model development and model evaluation in natural language processing. And these benchmarks have pushed major advances in natural language processing models. So these are screenshots. These might be slightly outdated, but these are screenshots from the GLUE and SuperGLUE leaderboards. And we can see that benchmark models have reached or are almost close to reaching human parity on these huge data sets and benchmarks. But one thing that we need to keep in mind when we build models for these benchmark datasets and evaluate them on benchmarks is that benchmark datasets are always going to be samples from all of the free text that is available in the world. And so what this means is that there are always going to be some domains and phenomena that will be kind of underrepresented in benchmarks just because they are low frequency. So benchmarks have this property kind of drawing back an analogy to Zipf's law, where they contain a high proportion of cases that all share a bunch of common high frequency phenomena. And there's a very long tail of phenomena that are slightly rare or more complex, but don't get as much attention just because they're much fewer in number. So what do we do with this long tail that we are kind of underrepresenting and sidelining in our most popular benchmarks in natural language processing? I just want to quickly explain how we are conceptualizing this long tail in natural language processing. So there are two ways of looking at all of these phenomena and domains that get pushed into the long tail. One view is they can be categorized into different groups based on some macro attributes that they share. This can be things like what language the text is in, what genre the text represents, what are the topics that the text covers. And by cutting up the space of all corpora along these macro dimensions, we can identify which portions of the space are low frequency or have received less attention in most of the benchmarks and models that we build today. Another way of looking at the same space is to look at text from the perspective of which linguistic phenomena it contains, which is a more micro level view. So there can be a bunch of different phenomena like negation, numeracy, discourse deixis that are much rarer in all of the large scale benchmarks that we look at today. Of course, these two views are not completely disparate. They are linked together. because certain kinds of domains tend to have higher frequency of certain phenomena. So one example, which I think I also mentioned in my internship presentation, is that the phenomenon of negation is much more prevalent in clinical EHRs, because when patients come in, doctors tend to write a ton of observations about the patient does not have XYZ. So if you look at typical NLP data sets, negation might not be that frequent, but in clinical EHR, negation is actually very frequent. So in this way, the macro and micro views are not totally separate, but they are intrinsically linked to each other. Another thing is that the macro level information about what the membership of a data set is more easily accessible, because people who create data sets tend to explain where they extracted the corpora from, which gives you clues about what the genre and topic information related to that corpus is. On the other hand, most datasets do not really report a laundry list of what linguistic phenomena they have covered. And so the micro level information is much less accessible, even though these days we are seeing more of an emergence of datasets which release a few examples from the dev set and test set annotated with different linguistic phenomena. That is still not a very mainstream thing to do. So for the most part, uh, our work has been focused on treating these macro dimensions as a proxy for studying micro-level linguistic phenomena. So our hypothesis here is that if we study domains and genres of text that have been underrepresented in traditional benchmarks, you will, by proxy, also bring more of the linguistic phenomena that have been sidelined uh, under the current benchmark paradigm under our purview. So, what are the big research gaps that arise due to the existence of this long tail in natural language processing? The first one is that we must adapt benchmark based models to these long tail domains. And one big issue that arises here is that long tail domains are often domains in which we don't have a lot of data, especially annotated data. So, the adaptation that we do here must be done under data scarce settings. The second big research gap is that there isn't a lot of focus on developing data sets and models that focus specifically on certain micro level long tail phenomena that is a slightly underexplored area. And the third big research gap is that benchmark model evalu because we've been focusing model evaluation primarily on benchmarks, we are sometimes over optimistic, and we do not have a clear picture of the generalization abilities of our benchmark trained models to different long tail domains and phenomena. So we've done some work in each of these three areas, but for today's talk, I'll primarily be focusing on the first question, which is how do we adapt models which have been trained on benchmark datasets to long tail domains, especially in scenarios where you don't have a lot of annotated data. And as a case study, I'll be looking at the task of information extraction from clinical text. Why information extraction and why clinical text? So information extraction is a very interesting task from a linguistic perspective, but it also has a lot of real world utility because IE can be used as a way to distill key information from lots and lots of documents, like say the entire index of Semantic Scholar, and to make it more accessible to lay people and as well as experts. And similarly, clinical text is interesting from a linguistic perspective because it poses a lot of challenges, like the use of highly specialized technical vocabulary that it is almost impossible for models to learn from standard benchmarks that are typically trained on news and Wikipedia. But also, most notably, it suffers from scarcity of annotated data and very rigid data sharing restrictions that make proliferation of clinical data difficult. So this is a quick outline. As I mentioned before, the tasks that I will be primarily focusing on are clinical event and entity extraction and low data regimes. But a lot of the techniques that I'm going to be talking about will be more broadly applicable to other information extraction or text classification tasks, as well as to other domains. In the first part of this talk, I'll be talking about a method that we recently proposed for unsupervised adaptation. That is an adaptation setting in which you don't have any annotated data from your target domain of interest. This method is called likelihood-based instance weighting, and I will explain the principle behind this method and analyze its performance on the task of adapting event extractors from news data to clinical data. And in the second part of the talk, I'd like to take a step back and compare a bunch of different popular adaptation methods on a broader range of tasks. So in this part of the talk, I'll be looking at both clinical entity and event extraction and compare all of the popularly used adaptation methods on a bunch of different data sets and try to see if we can figure out certain characteristics of adaptation methods that make them better choices for specific domains. And I will conclude by presenting some future directions that I see this research going into. And the key message that I'd like to sort of present by the end of this talk is that we have worked a lot on developing a huge arsenal of really strong adaptation methods through the years of research and transfer learning, but we still lag behind in developing a very good systematic understanding of their strengths and weaknesses and choosing which adaptation methods would work best on specific domains. So let's jump into the likelihood-based instance weighting technique. As I mentioned before, we are looking at an unsupervised adaptation setting. That is, we have no labeled data from the target domain. And instance weighting is not a new method. It has been a method that has been tried out in natural language processing for many years. And the key principle of instance weighting techniques is that you define a metric to measure similarity between the source domain and the target domain. And then you use this metric to weight the data that you have from your source domain that looks more like the target data higher. So say you have a source data set, what you would do is use the similarity metric between your source and target domains to compute weights between the source and to compute weights for each of the source instances, and then use these weights to train the model. And because you've given higher weights to instances from the source that look more like the target data, the idea is that you would learn a representation that would do better on the target data. In prior work, which has done this in a supervised setting, the way they learned the similarity metric was by training a model on the target data. Again, because they did it in a supervised setting, they had access to some label data from the target domain. So they ran this, they trained a model on the target data, and then they ran this model on the source data. And whichever instances this target trained model was able to get right were given higher weights because those are the most similar to the target data under the classifier model. In our case, because we want to do this in an unsupervised manner, we try to leverage language model likelihood. This is something that has shown success in out-of-domain and out-of-distribution detection tasks, so we decide to leverage it in an instance weighting paradigm. So basically what we do is we take all of the instances from the source data set and we give it to a language model that has been trained on the target, on unlabeled text from the target domain, and then compute likelihood scores for each of these instances. Based on these likelihood scores, the instances that have a higher likelihood are assigned a higher weight based on the calculation as shown in the slide. And then we train a model using these highly weighted samples, which are more lexically similar to the target domain. So in order to evaluate this likelihood-based instance weighting technique, we look at the task of adapting event extractors from news datasets to clinical datasets. And we look at two different kinds of clinical datasets. The first dataset is a dataset of clinical EHRs, which are annotated with events. And the second is a dataset of transcripts of conversations from doctor-patient visits, which again is annotated with events. So we constructed these two data sets for the project, and we did this by adapting the coding guidelines from the TimeML data, from the TimeML annotation scheme used for TimeBank. I'm skipping the details for the time being, but these are some examples of what the data in both these domains looks like. And this is a quick overview of the test set statistics for each of the three datasets that I just described. As you can see, all these datasets are fairly comparable, except for the fact that both the clinical datasets have a much higher diversity in the event vocabulary. In addition to evaluating the performance of our likelihood-based instance weighting technique, we also compare it against a bunch of different baselines. The first one is a zero-shot baseline where you just train it on the news data and test it on clinical notes and conversations without any adaptation. The second baseline is adversarial domain adaptation, which is also an unsupervised domain adaptation technique. So just a quick refresher for people who may be unfamiliar with this method. The adversarial domain adaptation framework consists of three different parts: the representation learner, event classifier, and a domain predictor, which is the adversary in this scenario. The goal of this framework is to train the representation learner to learn representations in such a way that they are good for the event classification task, but bad on the domain prediction task. And to do this, you can use a two-step alternating optimization process. In the first step, you train the domain predictor, which is also your adversary, on the task of domain prediction. And in the second step, you train your event classifier and representation learner models using this loss function, in which the first term ensures that you're doing good at the task of event classification, and the second term, which is subtracted, is the loss from the adversary, which ensures that you do badly on the task of domain prediction. So the end goal is that you learn more generalizable representations in the representation learner module. And the second baseline that we looked at aside from adversarial domain adaptation is domain adaptive fine-tuning. This is a pre-training based baseline, and this was shown to be useful for sequence labeling tasks previously in an unsupervised setting. So we try this out here as well. And the way this works is we mix unlabeled data from both the source and target domains and pre-train a language model on the masked language modeling task. In addition to the masked language modeling task, which is what previous work used, we also tried a different variant, which we called the syntactic variant. And this syntactic variant tried to do the pause tagging task instead of doing masked language modeling. And our hope was that because it's learning to predict pause tags instead of words, it might be learning features that are a bit more general, which did not really work out, but I'll go into that in more detail in the results. And aside from these three baselines, we also evaluate the performance of our likelihood-based instance weighting technique. So this is the performance of the four models that I described previously and the zero-shot baseline on the notes dataset. The rightmost bar graph is our model and the leftmost one is the baseline. As you can see, our method did improve performance on the domain as compared to a no adaptation baseline, but it was not the state-of-the-art method. Adversarial domain adaptation performed best. When we looked at performance on the conversations, we saw that our method improved performance again, but this time pre-training was the best performing method, and our method was a little bit worse than that. But one thing that we were interested in is, even though we did not do better overall as compared to some of our other baselines, are there classes of examples or instances that our method does better on? And is that tied in some way to what is the kind of variation present between the source and the target domain that we are looking at? So to do this, we looked at two kinds of linguistic variation between the source and target domains. The first dimension of variation that we looked at was lexical shift, which manifests in clinical text as the presence of highly technical terms, as well as terms that have a drift in meaning when they are used in clinical contexts versus when they are used in news context. So an example of this is the word periods, which typically refers to times in news, but refers to different things in clinical notes. And the second dimension of variation that we looked at was semantic shift. And semantic shift is basically a difference in event types because the context that the event occurs in is different. So an example here would be in the clinical conversations, there are a lot of times when the doctor or patients are thinking out loud or they're making hypothetical statements or questions and requests. So the kinds of events that occur in these sentences are very different from the kinds of events that occur when we are looking at narrative text like the news articles or the clinical records. The lexical shift is a lot more pronounced in clinical notes, whereas the semantic shift is a lot more pronounced when we're moving from news to clinical conversations. So when we looked at variation under lexical shift, what we did is we looked at model performance on in-vocabulary events and out-of-vocabulary events separately. And surprisingly, we noticed that out of vocabulary F1 on the clinical notes was much higher than the conversations, which is uh, kind of the inverse of what we would have expected because the notes vocabulary is much harder. But then, except for the pre training based model. But then we decided to poke more into this and look at what were the kinds of out of vocabulary events that models were getting right. And we saw that around 55% of these out of vocabulary events that models are getting right followed a bunch of common morphological patterns, specifically these three patterns, which are very good indicators of eventiveness. So typically, all kinds of past tense verbs that end in ed usually refer to events. And it seems like because all of these models are BERT based and BERT can incorporate subword information, it seems like they're exploiting these morphological regularities as tricks to be able to generalize to out of vocabulary terms like excision, wheezing, and irrigation, even though those are terms that has never seen in the news data set before. And we observed that adversarial domain adaptation was particularly good at bridging this vocabulary gap. These kinds of common morphological regularities were a lot more prevalent in the clinical notes than the conversations, which sort of explains why the out of vocabulary F1 was often higher on the notes. And we also looked at variation along the semantic dimension. And to do this, we did an ANOVA analysis with the event types from the data sets. And we compared, uh, and the comparators that we had were domain, event type, and the model. And we did see significant interaction between the domain event type and model event type, indicating that different models did better on different classes of event types. So we did a student post hoc analysis of the performance of each event type in each domain. And we saw that our method outperformed other models on two specific event types, long-term states and intentional states in the clinical notes. And this was an interesting observation because these two event types, unfortunately I had to skip this when I was talking about the annotation process, but these two are event types that are unique to the clinical notes and clinical conversations and never appear in the news domain. So these are totally unseen event types, and this is probably the purest form of zero-shot adaptation. So just a quick summary. Our proposed method, likelihood-based instance weighting, did improve performance on both domains, even though it did not beat some of the other unsupervised adaptation baselines. But it did manage to reach nearly 70 F1 without requiring any label data from the target domain, which indicates that it is a method that can be applied in various settings in which we want to rapidly develop information extractors when we have very little or scarce annotated data. One example where this might interface with recent work from Semantic Scholar is the work that was done on extracting COVID-19 mechanisms from scientific literature. And in such a setting, we can try to use these kinds of adaptation methods to make the mechanism extraction more accurate without requiring a lot of annotated data. And the final and most important observation was that different methods seem to do better at different kinds of examples or at different categories of linguistic variation. So we saw that adversarial domain adaptation was doing better at adapting at the vocabulary level, whereas our method was doing better at adapting to unseen event types. So this led to a very natural question. Is it possible to group different kinds of adaptation methods into categories based on what the underlying principle behind the adaptation method is, and try to figure out what properties make them work best on certain domains or tasks? So to do that, we decided to take a step back and systematically study the performance of popular categories of adaptation methods on a broad range of clinical information tasks. But before we do this, we need to actually know what are the popular categories of adaptation methods and what are the principles underlying them. So to do that, we did a qualitative meta-analysis of transfer learning research from the past 20 years or so. To do this meta-analysis, first we need to actually collect a bunch of papers on transfer learning research, and we did this from the December 2020 dump of STARK, which is a Semantic Scholar Open Research Corpus that was developed here. We specifically focused on 9 different star CL venues, which resulted in a set of 25,000 papers, from which we filtered out, from which we kept only papers that had domain adaptation or transfer learning in the title or the abstract. We did not look for papers that had domain adaptation in the body because a lot of papers tend to discuss domain adaptation in the discussion section or have a small experiment, but not really focus on that as the key contribution. After collecting these 392 papers that were focused on transfer learning and domain adaptation, we decided to whittle it down to construct our final meta-analysis sample of 100 papers. And this Prisma diagram indicates how we screened different abstracts and constructed our final sample. So in the first step, we just removed all of the duplicate abstracts. And in the second step, we did some key filtering steps. Because we are interested in looking at adaptation methods in the NLU setting for various tasks, we excluded all of the abstracts that had a focus on generation-specific tasks. We excluded all abstracts that were only proposing data sets and no adaptation methods. And we also excluded papers that had no focus on adaptation or had more of a multimodal focus. And at the end of all of the screening, we ended up with a set of 266 abstracts that we found to be eligible for our meta-analysis. And from this, we constructed the final meta-analysis sample of 100 abstracts using 2 inclusion criteria. So the first one was that we included all of the abstracts which had more than 100 citations because those are highly cited, probably transformative works in the field that we definitely need to look into. And from the remaining set, we removed all the papers with no citations and sampled the rest randomly until we reached n equals to 100. And the reason we did this kind of a two-step sample construction was because we wanted to balance between highly cited work and topic rarity. We did not want to sideline work that focused on non-mainstream domains or non-mainstream data sets because those would typically get cited less. The other aspect that we also wanted to take care of was temporality because more recent papers tend to have fewer citations and we wanted to make sure that we did not totally exclude those. So at the end of this sampling process, we had 100 abstracts that we included in the final meta-analysis sample. And then I just want to briefly go over the structure of our meta-analysis to indicate what was the kinds of information that we recorded for each of these papers. So the first thing that we recorded was what is the task studied in the paper. And here we group tasks into 11 different categories based on the structure of the task as well as what kind of linguistic information is required in order for models to actually do the task. We also cataloged what were the domains studied in that paper and the datasets that were used for each domain. We also cataloged what was the baseline task model that was used for the task, whether it was neural or non-neural, and we excluded any modifications that were made to the architecture for the purpose of adaptation. The fourth thing that we cataloged, and this is probably the most important thing, was what was the adaptation method that was proposed, extended, or applied in that paper, and not only identifying what was the adaptation method, but also categorizing it according to a taxonomy of adaptation methods. This taxonomy is largely borrowed from a recent survey paper on neural unsupervised domain adaptation in NLP. But we had to extend it a little bit because we are looking at more adaptation methods that are non-neural as well as look at supervised domain adaptation. So broadly, the taxonomy divides adaptation methods into 3 different categories: model-centric, data-centric, and hybrid, which are fairly self-explanatory labels. Model-centric approaches try to do adaptation by modifying the task model. Data-centric approaches to adaptation by trying to manipulate the data distributions of either source or target domains. And hybrid methods are ones that do not cleanly fit into either of these 2 categories. Under model-centric, there are 4 subcategories. Feature-centric methods form the first category. And under feature-centric methods, there are 2 subcategories: feature augmentation and feature generalization. Feature augmentation techniques are ones where The model tries to learn an additional set of pivot features to transform from the source to target domains, and then concatenates this additional set of features into the original task model. And feature generalization methods are ones that try to learn a joint shared space between both the source and target domains. The second category of model-centric methods is loss-centric methods that try to edit the loss function in order to do better domain adaptation. And under this, we have the category of loss augmentation approaches. So if you remember the adversarial domain adaptation method, that would fall under this category. The goal here is to add additional terms to the loss function that promote generalization. The third category under model-centric is parameter-centric approaches, and under parameter-centric, there are three different categories. Parameter initialization, which in some ways introduce an inductive bias by initializing the parameters for the target from source trained data or using some human known priors. The second category is addition techniques, which work by adding extra parameters at different places in the model in order to make adaptation easier, and sometimes this can even be used to do adaptation more efficiently by only fine-tuning those parameters. And the last category of parameter-centric techniques is freezing, where the goal is to freeze different parts of the model in order to avoid it, in order to prevent it from overfitting to the domain that it's being trained on. And the last category of model-centric approaches, which is one that we had to add. So basically all of the edits that we had to make are highlighted in yellow, so you could figure out what those are. The last category that we had to add is ensemble approaches, and these are more common in multi-source settings where you have multiple data sets from different source domains that you want to learn a model from. And this includes stuff like mixture of experts methods that can take multiple source domains into account. Under the umbrella of data-centric approaches, there are 5 different categories. The first one is pseudo-labeling approaches, which function by generating weak supervision labels for a lot of the target data based on some training or supervision from the source domain. The second set of methods is active learning, which also function by trying to by trying to obtain labels for some examples from the target data. But in this scenario, the examples are actually provided by human experts. The third category of approaches is noising or denoising, where the source and target distributions are manipulated by adding noise or by removing noise in order to bring them closer to each other. The fourth set of techniques is instance learning techniques, which function by trying to map out all of the source instances which are in the neighborhood of specific target instances and trying to leverage those when making predictions. And the fifth category under data-centric techniques is pre-training, which probably needs no introduction. And it's basically trying to train large language models on combinations of source and target data and using them for the adaptation process. And finally, under the hybrid category, there are 2 subcategories, instance weighting and data selection, which are kind of similar in the sense that both of them can be seen as methods that edit the loss function, but also can be seen as methods that manipulate the data distribution by promoting oversampling or undersampling of specific instances. So this is the overall taxonomy that we'll be following for the rest of the meta-analysis. And just to put this into more perspective, the 3 methods that we used in the previous event extraction work, likelihood-based instance weighting, domain adaptive fine-tuning, and adversarial domain adaptation would fall under these categories in the taxonomy. This slide and the next slide has a few examples of what adaptation methods would fall into each category, but I'm just going to quickly skim this for the time being. We can revisit this if people are interested later. In addition to what are the adaptation methods used in the work, we also cataloged stuff like what are the other baseline adaptation methods that this method was compared against, what are the adaptation settings in which these methods were tested, was it unsupervised, did they look at multiple source domains, was there variation in the label space, etc. And we also noted down a summary of the results, especially focusing on things like, was this adaptation method best across all source target domain pairs? If not, were there specific pairs that it did better on? And was there any additional analysis as to what sets of pairs it worked well on? So based on this structure, we went through all of the 100 papers and coded all of the adaptation methods used in them. So these graphs give a brief summary of the most frequently used adaptation methods across all the 100 papers that we had in our sample. The graph on the left-hand side um, gives a summary of all the adaptation methods by course label, which is the first layer in our taxonomy, that is either model-centric, data-centric, or hybrid. And the graph on the right-hand side gives a summary based on fine labels, which are basically the leaves in our taxonomy. And as you can see, model-centric methods tend to dominate, like about 60% of the work that we looked at used model-centric approaches. But if you look at the distribution of techniques by fine label, you can see that pre-training is starting to catch up, and it's the third most popular technique. In addition to looking at what were the most frequently used adaptation methods across all domains, we also looked at papers which tested the adaptation methods they proposed or used on at least one expert domain. Here, expert domains are basically the class of all domains that use specialized or technical vocabulary. This can include domains like biomedical text, clinical text, scientific literature, etc. And as you can see, the top four methods are not really very different. Here also we had feature augmentation, loss augmentation, pre-training, and pseudo-labeling in the top five, and we have those here as well. The only difference is that parameter initialization gets replaced by instance weighting. And this kind of makes sense because parameter initialization typically requires you to have a lot of, or at least some available related source data sets, and that's often not the case when you're looking at expert domains. So for our systematic study, we decided to look at these top five categories of methods, but because we're looking at an unsupervised setting, we can't use feature augmentation techniques because they require some label data from the target to train the additional weights for pivot features. So we look at the remaining four categories of methods that we have, which includes pseudo-labeling, loss augmentation, pre-training, and instance weighting. Under pseudo-labeling, we are looking at the self-training paradigm, which I'll explain in more detail on the next slide. Under loss augmentation, we are looking at adversarial domain adaptation, which I've already covered before. Under pre-training, we are looking at continual pre-training, kind of similar to the Don't Stop pre-training paper. And under instance weighting, we are looking at classifier-based instance weighting here, and I'll cover what that means and why we decided to make this choice. So this is a quick overview of the self-training algorithm that we are looking at in this study. As you can see, in the first step, we train a model on the label data that we have from the source domain, and this model becomes our teacher model. This teacher model is then run on all of the unlabeled data that we have from the target domain, and it's used to generate a bunch of labels for all of those unlabeled instances. Here, we can choose to keep the labels for all the unlabeled instances, or we can only focus on a certain proportion of high confidence certain proportion of instances for which the labels generated are high confidence. And then using this unlabeled data as well as the label data from the source domain, we train a new student model to minimize cross entropy across both these data sets. And this student model then becomes the new teacher model and regenerates labels for the unlabeled data. This process can be done iteratively until you either exhaust all of your unlabeled data or you reach certain confidence threshold. And the second difference, which is we looked at classifier-based instance weighting instead of likelihood-based instance weighting. So here, instead of using a language model to look at the source instances and assign them weights, what we did was we trained a classifier to predict whether an instance is from the source or target domain. Again, this classifier does not really need annotated data from the target domain. You can just use unlabeled data. And then we ran this domain classifier on the source domain in order to identify with what confidence this model said that the instance belonged to the target domain. And once that had a higher confidence score of falling into the target domain or a higher probability score of falling into the target domain, were given higher weights. The reason we did this was we wanted to experiment with a setting in which we can change the weights of the instances after each iteration of model training. And usually it's a bit more expensive to retrain a language model at each phase. And so instead of that, we decided to do this kind of a setup where we could retrain the domain classifier after each phase.
Excuse me, Aakanksha. Can you remind me how many domains were used in the training of this? Like how many domains you were considering when using this domain classifier?
2 domains at a time.
Just two. Okay.
Yeah.
Thanks.
So the tasks and data sets that we looked at in this study, we looked at 2 main tasks, entity extraction and event extraction. The source domain data sets that we used for both of these tasks, for the first one, it's the Cornell 2003 dataset, and the second one is the Time Bank News dataset. Both of these data sets are English news narratives. These are the target data sets that we used for both these tasks. For entity extraction, we used I2B2 2006, 2010, and 2014. 2006 and 2014 data sets from I2B2 are tasks on clinical de-identification. So the goal is to identify attributes of protected health information, which could be things like what hospital the patient was admitted in, the patient's name, age, etc. So the entity types that occur in these nodes that we have to identify are fairly similar to the Cornell 2003 task, which is focused on identifying named entities like people, locations, organizations, etc. On the other hand, the I2B2 2010 dataset is a medical concept extraction dataset. So the kinds of entities that it focuses on are just problems, tests, and treatments. And this is a much more distant transfer task from news as opposed to 2006 and 14, because there's no mapping between the label spaces. In the second task, which is event extraction, the 2 target datasets that we looked at are I2B2 2012 and empty samples, which is the event extraction dataset from the previous uh, set of experiments on likelihood-based instance weighting. Because of this situation where certain data sets have a label mapping with the source, but the I2B2 2010 dataset does not, we evaluated the NER task at 2 different granularities. The first one is coarse evaluation, where you just predict the entity boundaries and do not predict entity types at all. And the second evaluation is a fine evaluation, where you do predict entity boundaries alongside entity types. So in the coarse setting, we can evaluate on all 3 datasets, but on the fine setting, you can only evaluate on 2006 and 2014 because on 2010, we don't have a mapping between entity types. And we are evaluating all of these methods in an unsupervised setting, so we don't have any label data from the target domain. So this is a quick overview of the results that we had for all the different methods. On the NER datasets in the course setting. Zero shot is basically indicating what was the zero shot performance if we did not use any adaptation on top of the baseline there. So here we can see that pseudo-labeling does best on both 2006 and 2014 in terms of F1 scores. On 2010, it does really badly, and I2B2 and loss augmentation, which is the adversarial domain adaptation method, does best on I2B2 2010. When we look at fine, we see that pseudo labeling is still the best performing method on 2014, but on I2B2 2006, loss augmentation is now the best performing method. And when we looked at event extraction, we saw that loss augmentation was generally the best performing method across all the across both the data sets that we were looking at.
Excuse me, Aakanksha.
Yeah.
Do you mind going back a couple slides to the I2B2 results? So thanks. The magnitude of the scores are quite different across these data sets, and I'm unfamiliar with these data sets, so I'm kind of curious to understand what's changing so much between these years under this sort of same thread, like data set.
Yeah.
I guess thread. Yeah.
Yeah. So one difference is that even though 2006 and 2014 are on the same task, the underlying sets of nodes come from different clinical not specialties, come from different clinical systems. So in I2B2 2006, the data was primarily from Partners Healthcare, and on 2014, they expanded which different hospital systems they were getting their clinical notes from. That's one big difference. And the second difference is that in 2006, they had a much more compressed set of tags as opposed to 2014. So in 2014, they had 18 different course tags, which were grouped into 7 broad NER tags, whereas in 2006, I think they only had 4, if I'm remembering correctly. So I think what happened in 2006 was a lot of entities that got split into different categories in 2014 were not necessarily split. It were just combined into a single category when we were looking at 2006. So that might have led to some inter-class confusion.
I see. By splitting out these categories, presume maybe the task got easier, which explains the higher scores.
On 14, yes. And 2010 is totally different because it's looking at medical entities.
I see. Okay.
Just for calibration, can you say what this, or do you know what the scores might look like if you had a small amount of labeled data from the target domain?
So I don't know about a small amount of label data because that's the next set of experiments I'm planning to do. But given the entire supervised data set, it's around 86 for I2B2 2010 and between 85 to 89 for 2006 and 14. So it's fairly high. But I'm trying to do some experiments where you don't use the entire supervised data, but only look at a small amount of it and see how much can you get.
Thanks.
Yeah. And so in summary, what we observed was that the loss augmentation set of techniques like adversarial training did best on the event extraction task, but both adversarial training and self-training did well on NER with trade-offs between the both. The biggest observation was that self-training works better for closer transfer tasks because it had really poor results on I2B2 2010. And this is not a super surprising observation because self-training has this issue that it will reinforce the kinds of predictions that it has learned initially because the initial model is the one that generates more and more data for you. So if the initial model is not super accurate or if there are huge blind spots that it has, then it's likely to propagate those errors as you do self-training further. But it is interesting that self-training techniques are working so much better now because when I was doing my meta-analysis, some of the earlier work on applying self-training to parsing showed very limited gains from self-training or sometimes even negative results. And one thing that we saw, but we don't really know why that's happening, is the slightly lower performance of pre-training than we expected. We think that there might be some level of forgetting going on, so it might work better if we had a different mixture of source and target data where we possibly weight either the source or the target data higher, but that's something I'm trying to poke into a little bit more. So yeah, that's basically what I wanted to cover in terms of our work on adaptation to long tail domains. Aside from that, there's also some work I've done in looking at the other research gaps that I mentioned in the beginning of the presentation, which basically look at other aspects of the long tail. So we've done some work on developing data sets and models for long tail linguistic phenomena. And under this umbrella, I've looked at numeracy and NLU models as well as temporality in the context of event extraction, especially at the document level. And I've also looked a little bit at trying to do more fine-grained, linguistically motivated analysis of NLU models beyond looking at their performance on benchmarks to understand what their strengths and weaknesses are, which was the third research gap that I mentioned before. So where does all this leave us and where do I see this research work going in the future? So one thing that I'm really interested in, especially after doing this meta-analysis manually, is there a way to automate doing these kinds of meta-analysis? Because long tail is going to be a persistent problem in natural language processing. So even if we expand expand to some newer domains as opposed to the ones that we're looking at right now, there will always be certain domains that get sidelined. So it seems like this is something that has to be done periodically. Like we need to periodically stop, look at what we've been doing so far, categorize all of the methods that we have and understand their strengths and weaknesses. But doing this manually requires a lot of effort, especially considering the volume of research that we have right now. So is it possible to automate such meta-analyses to some extent so that we can more systematically identify future gaps that we want to pursue? And I think Semantic Scholar has started to make some headway in this direction by developing data sets for deeper QA on natural language processing papers like Casper. Another thing which also kind of ties in with my internship project is I'm interested in using literature or information from literature as a source of external knowledge for various tasks. So something that I didn't really go into in much detail in this presentation is my work on temporality, in which we were trying to look at using different sources of external knowledge, and literature is one of them. That I'd be interested in looking at more. I also explored this in the context of different clinical outcome prediction tasks in my internship project, which I think you guys have heard me speak a lot about. And finally, and this is probably more of a stretch goal or a long-term goal that I'm interested in, is to study how scientific knowledge evolves over time and how the things that we think were true get
Let's just wait a little bit for the.
Kind of like Bilbo at his birthday party.
sorry about that. I did not realize.
No problem. Do you mind sharing? I think we
Yeah.
it cut off roughly when you were talking about sort of the further long-term goals.
Okay. So this slide?
That's right.
So I'm not sure at what point I cut off because.
I guess, do you mind going from when you start talking about sort of longer-term goals after discussion about like literature review?
Okay. Yeah. So the other direction that I have also been interested in, and maybe a bit more recently, is trying to use literature as a source of external knowledge to augment different methods. So I've been looking at various kinds of external knowledge sources for different projects, especially the work on temporality. But I feel like we can also use all the information and evidence that's present in literature when looking at different information extraction or classification tasks. And the internship project that I did at Semantic Scholar this summer kind of focused a little bit on this from the perspective of improving performance on downstream clinical outcome prediction tasks. And finally, the last and maybe a bit of a stretch goal that that's maybe more long term, and something I'm interested in doing is studying temporal evolution of scientific knowledge. So things like what were things that we thought we knew but we've since disproven, or what are the paths that we think are most likely to lead to more progress, and trying to do more science of science stuff. But one common denominator that underlies all of these future research directions is low resource information extraction. And I think we need to develop much better capabilities for doing low resource IE if we want to reach a point where we are able to automate these kinds of processes uh, with a measured amount of human effort required. So I think this is a common denominator, and that's why I've been focusing on it a good amount in my research. So yeah, thanks to all of my wonderful collaborators, and thank you all for your time today. And if you guys have any more questions, I can take them now. And hopefully I don't drop off the call again.
Thanks, Aakanksha. Let's thank the speaker first for a great talk. And questions. Yeah, feel free to just unmute and ask a question. I have one, but I'm waiting for to see if other people. Okay, I'll ask it. Aakanksha, in your results on the meta-analysis, I guess the message that I sort of got from the results is I didn't see like a single dominant method across all those data sets.
Yeah.
It seems like which method works best is very much a property of like the level of discrepancy there is between the transfer domains and just like the properties of the data sets themselves. And it makes me wonder if you've thought about like, I guess like how, as a practitioner, if I want to use these methods, how should I go about using your findings here? Because it seems like maybe I have no choice but to try them all.
Yeah, that's a really good question, and that's exactly what I want to poke at a little bit more. So one thought I have is there a way that we can define some sort of distance between the source and target domains, and then see whether that correlates with performance increase in different techniques that I tried out? So I'm not sure if there was a recent survey, I think last year, don't remember where it was, but they basically had this huge summary of what are the different kinds of techniques you can use to measure differences between source and target distributions when you're looking at domain adaptation. And I want to do a kind of next step to this experiment where I try out all of those different metrics between the source and target and correlate them with performance of different modeling categories, so that when you get a new domain, you can run all of those metrics, see where your see where the distance between the source and target domains lands you in the space, and then you at least have a smaller class of techniques to try instead of being like, oh my god, I have to try everything.
Thanks. Lucy, do you want to ask yours?
Yeah, thanks for the talk. I think this is a fairly related question. So I liked your kind of proposal of these domain adaptation techniques as a way of, or I guess the kind of relationship between the macro phenomenon of, you know, something like domain difference to these micro linguistic phenomenon, and using the macro as a proxy for the micro. But I wonder, like during the kind of your review or your meta-analyses, did you kind of encounter it, sort of how maybe like any information about how well these studying something macro like domains actually corresponds to improvements in these like micro-linguistic phenomenon, or whether there's kind of potential for doing both at once, trying to evaluate both at the domain level but also at the phenomena level?
Yeah, that's a very interesting question. So that is something we were looking for, but and I think we have a small section on this in the paper, but not in the talk. But the problem is that a lot of methods that focus on domain adaptation only focus at the macro level and don't really do an analysis at the micro level. So even if they get some small gains on the domains that they're evaluating on, they don't really say what were the kinds of examples that were present in the domain, which is the kind of information we would want if we wanted to look at the micro level linguistic phenomena. So that was one of the things that we pointed out as we need to do more of this. And that's why we kind of did it for the EACL work that I talked about, where in addition to just looking at the improvements that each method gave you, we also looked at what were the kinds of instances that fell into those categories. But I feel like with the current paradigm that we don't have enough information based on work that people have done. It's definitely something that we need to work on more in the future.
Yeah, seems like there's a lot of potential there. Thanks.
It is 11:02. Were there any questions that people wanted to get in? Okay, well then let's thank the speaker again for a great talk. Thanks so much, everyone.
Thanks.
Thank you.
Thanks, Aakanksha.
I don't know if someone has to stop the recording or if it automatically
Just
stops.
leave. It'll
Okay, just leave.